Good evening, everyone. Welcome to the tutorial on solving differential equations using MATLAB. I am Priyanka Shukla, and I'll be presenting today's session. With me, I have Shagdara Bhattacharya and Suraj Kumar, who will be moderating the chat. We are from MathWorks, the makers of MATLAB and Simulink, our key products. MathWorks is the leading developer of mathematical computing software for engineers and scientists. Here are some industries where our tools are being used extensively: aerospace and defense, automotive, biotech and communications, to name a few. Here's what we will cover in today's session. We'll start with a quick recap of differential equation and the types to set the foundation. Next, we will see the MATLAB ODE solvers and how they help solve these equations numerically. In today's session, we will use the example of skydiver's motion to demonstrate how to model and solve differential equations using MATLAB. We will use ODE 45, ODE 23, and PDE Modeler app. We will wrap up the tutorial by summarizing the key takeaways, followed by a Q&A session where you can ask questions or clarify any doubts. This session is designed to demonstrate how MATLAB products can be used to solve and visualize differential equations numerically. The focus will be on practical application and implementation, and not the underlying theoretical concepts of differential equations. In this session, we will use ODE solvers like ODE 45, ODE 23 to solve the first order and second order differential equations. We will also solve the differential algebraic equations using MATLAB, incorporating the mass, matrices, and algebraic constraints. We will simulate the wave equations and analyze oscillatory behavior using the PDE Modeler app. We'll use MATLAB to model, solve, and visualize solutions for ODEs, DAEs, and PDEs. As you all know, differential equation is a mathematical equation that involves an unknown function and its derivatives. It describes how a quantity changes over time or space. They are essential because they help us model real-world phenomena such as population growth or electrical circuits. They also help predict the system behavior, like how a spacecraft moves, how a disease spreads, or how heat transfers. They also help design and optimize the engineering systems, such as car braking systems, control systems, and signal processing. Differential equations can be divided into various categories based on order, linearity, homogeneity, and partial derivatives. In today's session, we will focus on first and second order differential equations and partial differential equations. For this, we are going to use the MATLAB ODE solvers. The ODE solvers are built-in functions that numerically solve ordinary differential equations. They use various algorithms to approximate solutions for initial value problems, making it easier to analyze dynamic systems that cannot be solved analytically. In this session, we will concentrate on ODE 45 and ODE 23. So this is what we are going to do in today's session. Let's consider a problem where we want to model the motion of a skydiver during their descent, both before and after deploying a parachute. This requires understanding how the forces like gravity and air resistance act on the skydiver and how these forces influence their motion at different stages. The first stage involves the free fall before the parachute deployment, where the motion is governed by Newton's second law. The equation for free fall with air resistance is a second order ordinary differential equation, which we convert into a system of first order ODEs to solve numerically. In the second stage, the parachute is deployed and the forces change abruptly. This introduces constraints like equilibrium conditions, and the system must accommodate varying initial conditions based on the type of parachute and air resistance. Finally, the third stage accounts for external environmental effects such as oscillations due to wind forces. These oscillations can be modeled using wave equations, and the ODE solver can include additional factors like temperature and wind effects to improve the accuracy. Through ODE solvers, we can analyze and simulate these dynamics effectively to create a complete mathematical model of the skydiver's motion. In today's session, we will use the example of the skydiver's motion to demonstrate how to model and solve differential equations using MATLAB. However, please note that we won't be building a detailed physical model of the skydiver's descent. Instead, the focus is on showcasing the process of using MATLAB tools for solving similar real-world problems. This will give you the skills to approach such scenarios on your own. Now, let's go to the next part of the tutorial, where we will practice solving the differential equation using MATLAB. For this purpose, I am sharing a work live script which has placeholder codes. During the session, my colleagues will post the relevant codes in the chat window so that it is easier to follow along. At the end of the session, we will share the solution live script which you can use for your future references. To get started with the hands-on activity, please download the work live script shared in the chat. You can open the file in the MATLAB online provided for this course. To access the MATLAB online, please go to the NPTEL course page and navigate to the MATLAB Access section. The link provided in the third step will allow you to access MATLAB online. If you have not accessed MATLAB online before, please complete the steps mentioned on the MATLAB Access page. In case you are not registered for this course and are attending the session, you can download the work live script and open in licensed MATLAB online or MATLAB desktop version. Once you have downloaded the file and have opened the same in MATLAB, please put a thumbs up in the chat. I hope you are able to download the live script and open in MATLAB. If you are unable to download the live script or are facing any issues, please drop a message in the chat window. If you have downloaded the MATLAB, if you have downloaded the work live script, you have to access the MATLAB online. Please navigate to the course NPTEL course page, and there in the MATLAB access section, you can see 3 steps mentioned to access MATLAB online. In the first step, you have to create a MathWorks account if you already don't have an account. So please click on the link provided in the step 1 to create a MathWorks account. Once you create an account, you will get an email for verification. And once the email has been verified, you can please move on to the next step. Once you have completed the step 1, click on the link provided on step 2 to access the MATLAB that is provided for this particular NPTEL course. After that, you can come back to the step 3 and use the link provided here to access MATLAB online. Once you are able to access MATLAB online, navigate to the path where the work live script is downloaded and open it. You can also open the work live script in your MATLAB desktop version. For that, please open the MATLAB and then go to the Open tab and select the path where the file is downloaded. I hope you are able to open the live script in either MATLAB Online or MATLAB Desktop. Please put a thumbs up if you are able to do so. Please confirm if you are able to open the live script either in MATLAB Online or in MATLAB Desktop version. MATLAB Desktop version. We are sharing the file again. If you are not able to find the file, please try to download it once more. We have shared the file again. Please try to download it once more. I will wait for a couple of more minutes so that you're able to download the live script and work along with me. Then we'll resume the session. As most of you are able to download the live script, let's start with the hands-on activity. The agenda of today's session is to try to model the, the free fall, the parachute deployment, and the external environmental effects on a skydiver. For this purpose, we are trying to use the differential equation and solve them to see how this can be modeled. As I mentioned previously, we will use the example of the skydiver's motion to demonstrate how to model and solve the differential equations using MATLAB. However, we won't be building a detailed physical model of the skydiver's descent. Instead, the focus is on showcasing the process of using MATLAB tools for solving similar real-world problems. Let's get started. The first stage for solving is the, the free fall of the skydiver. The motion of the skydiver before deploying the parachute is modeled using Newton's second law. The equation governing the free fall with air resistance is a second order differential equation, which is then converted into a system of first order differential equations to solve numerically. We will use the MATLAB ODE 45 solver, which is designed to handle the first order differential equations. We usually convert a second order differential equation into a system of first order differential equation so that it becomes easier to represent more complex dynamics. And also, most of the numerical methods like Rangekutta work inherently with the first order equations. So, to model this motion of the skydiver, our first step is to convert the second order differential equation into a simple first order differential equation. For this purpose, we are going to assume a very simple first order differential equation dy by dt is equal to 2t. In this equation, the system, it describes a system where the rate of change of y with respect to time is proportional to 2t. To solve this simple ODE, we are going to use the ODE 45 solver. For this purpose, we are going to set up two variables, time span and initial condition. The time span represents the range of interest of time, and the initial condition uh, tells us that our system is starting from the rest. For this particular equation, the time span is 0 to 10, and the initial condition is y not equal to 0 because the system is starting from rest. So, in the code section, for the first line, let us add the time span. The time span is defined as t span from 0 to 10. For the initial condition, we will define the variable y0 is equal to 0 as our system is starting from rest. I hope you're able to follow along and have added the variables t-span and y0 in the code section. Now we are going to define the function to solve the differential equation using ODE 45. For this, in line 5, please enter this following code. When we are defining the ODE 45 function, we will specify the differential equation as well as the time span and the initial conditions. So for your reference, we have added the code in the chat window as well. I hope you were able to follow along and have added all the codes required in this particular section. Once you have added the 3 lines of code, come to the MATLAB toolstrip and click on Run section. I repeat, once you have added the required lines of code, click the Run section button on the MATLAB toolstrip. Put a thumbs up in the chat window if you are able to get the plot for this section. So the solution that you obtained from this example demonstrates that how numerical solvers like ODE45 can approximate solutions to the ordinary differential equations. For the skydiver, the free fall motion will result in a more complex system of equations. This simpler example serves as a stepping stone, demonstrating how numerical solvers approximate solutions and how MATLAB handles the numerical integration process. While the skydiver's dynamics are more integrate, the same principles will apply. Using ODE45, we can extend this process to simulate the free fall motion of the skydiver under the influence of gravity and air resistance. In this previous example, we solved the ordinary differential equation manually using ODE45. Now, we are going to solve the same equation using a live task. We are going to use the solve ODE task, which achieves the same results but with fewer manual steps, and also provides an interactive experience to specify the equation, initial conditions, and time span. To get started, go to the Insert tab on the MATLAB toolstrip and click on the Task dropdown. I will repeat, to add the Solve ODE task, go to the Insert tab on the MATLAB toolstrip and click on the Task dropdown. After clicking on the Task dropdown, search for Solve ODE. After clicking on the dropdown, search for Solve ODE. Click on this symbol to add the Solve ODE live task in the live script. I hope you all are able to add the Solve ODE task in your live script. Please give a thumbs up for confirmation in the chat window. The steps to open the Solve ODE task have already been added to the chat for your reference. I will repeat the steps once again. Go to the Insert tab in the MATLAB toolstrip and click on the task drop-down. You have to click on the task drop-down in the MATLAB toolstrip. Once you have clicked, you can see various tasks listed there, and in the search bar, you have to search for Solve ODE. You have to search for Solve ODE task. And then you have to click on the Solve ODE icon. I hope you're able to add the live task in the live script. If you have done so, please put a thumbs up in the chat window. Thank you. So now we want to solve the previous example where we had a very simple differential equation dy by dt is equal to 2t. For this purpose, first we will define the type of ODE being used. In this live task, we have 4 different options of the ODE type. Out of these 4, the first type, that is dy by dt is equal to f of ty, resembles the simple ordinary differential equation that we are trying to solve. So, as a first step for solving the ODE using the live task, click on dy by dt is equal to f of ty. I repeat, please click on the first option of the ODE type, that is dy by dt is equal to f of ty. Apologies, I'm facing a technical issues. Give me a couple of minutes. I'll unshare my screen and then share it again. Thank you. I'm sorry for disconnecting. As I was saying, We are going to solve the different we have added the first ODE dy by dt is equal to f of ty. I hope you were able to follow along till this step. The next step is to mention the ODE function. The ODE function that we are going to use here is the differential equation, the ODE solver, that is ODE 45. So click on the ODE function drop down and select the function handle. I repeat, click on the ODE function drop down and select function handle. Once you select the function handle, you can see a edit field where you can mention the function. For this, we are going to use the ODE 45, and in the edit field, we are going to first define the differential equation. So modify this edit field and type at the rate of t comma y and then 2 multiplied by t. I will repeat. In this ODE function, you have to function handle, and then in the edit field, you have the differential equation that you are trying to solve. So in the edit field, please type at the rate t comma y. After that, 2 multiplied by t. I hope you were able to follow along till this step. We will move on to the next step where we will add the initial value of y and also the initial time. Since this is a very simple ordinary differential equation that we have assumed, the initial value y0 is 0, as well as the initial time is also 0 because the system is starting from rest. Once you have added the initial value y0 equal to 0, you can see that in the specify solver options, automatically ODE 45 is selected. Now, let's come down to solve ODE dropdown. Come down to the solve ODE dropdown. Here you can see two edit fields for the start and end times. This allows you to select a time range over which the solution will be specified. We are going to change the end time from 1 to 10. I will repeat the steps that we have followed so far in this solve ODE task. First, we define the ODE type by selecting the first option, that is dy by dt is equal to f of ty. Then we selected the ODE function by function handle and have added the respective value. For the initial value of y0 and t0, we have specified 0. Then we have modified the end times in the solve ODE as 10. Once you have added all the required parameters, click on the Run button in the live task. You can see the plots that we obtained using the live task and the plot that we obtained by running the code are same. With this, we have completed the stage 1. Now, let's move to the stage 2, where we want to model the parachute deployment. When the parachute is deployed, the forces acting on the skydiver change drastically due to the sudden increase in air resistance. This introduces algebraic constraints such as equilibrium of forces, which must be satisfied alongside the differential equations describing the skydiver's motion. For this purpose, we need to use the differential algebraic equations, which are more complex than the regular ordinary differential equations. So, to simulate this stage, we need to solve these differential algebraic equations numerically, incorporating both the dynamics and the constraints. The differential equations will model the skydiver's velocity and acceleration, and the algebraic equations will impose the constraints like force equilibrium between the drag and gravity. We will use a singular mass matrix for this purpose. A singular mass matrix distinguishes between zero rows, which represent the differential equations, and zero rows, which represent the algebraic constraints. For this purpose, we are going to assume a system of differential equations mentioned here. Y1 dash is equal to y1 y3 minus y2. Y2 dash is equal to y1 minus 1. And the third equation, 0 is equal to y1 plus y2 plus y3. To solve these equations, we will rewrite the system in the form of m dy by dt is equal to f of ty. Once we have rewritten the system of equations, we are going to create a local function and mass matrix to represent the problem. For this purpose, let us define the required local function. I'm adding the code here, and the code has already been added for your reference in the chat window. We have defined the function ODE fun with the variables t and y. In the out, we have defined the output of the three differential algebraic equations. We have also defined the mass matrix variable with the required values. Please run this particular section so that the variables are available in the workspace for the later activities. For this, click inside the code and then in the MATLAB tooltip, click on Run section. I will repeat. We are currently in the second stage of modeling the skydiver's motion, and for that purpose, we have created a local function ODEFUN and a mass matrix. We have defined these variables and then we have run this particular section so that the variables are available in the workspace. I hope you have followed along till this point. Please put a thumbs up in the chat window if you have completed till this step. Thank you for responding. Now, we are again going to use the solve ODE task to solve these system of equations. For that, go to the Insert tab in the MATLAB tooltip, click on the task drop-down and search for Solve ODE. I will repeat. We are again going to use the Solve ODE task to solve this system of differential algebraic equations. For that purpose, please go to the Insert tab on the MATLAB tooltip and then click on the task drop-down. In the search window, please write Solve ODE and then click on the icon. We'll wait for the task to get added to the live script. I hope you all were able to add the task to the live script. Once you have added the task, please put a thumbs up in the chat window. Thank you for responding. Now, since we are trying to solve the system of differential algebraic equations in which the type is m dy by dt, we are going to select the second type for the ODE. I repeat, as we are trying to solve a system of differential algebraic equations which have the format of m dy by dt is equal to f of ty, we are going to select the second option in the ODE type. Once you click on this option, the related parameters will get updated. Now, come to the ODE function and in the drop-down, select function handle. I will repeat, come to ODE function f of ty and select the function handle. I hope you recall we had created a local function. So specify the local function here. The function name was ODEFUN. So here for the function handle, I am going to mention ODEFUN. Now, for the mass matrix M, click on the drop down and then select mass matrix. I repeat, for the mass matrix, click on the drop down and then select mass matrix variable that we had created previously. The initial value for this system of equations is 1, 1, and -2. So we will add this in the initial value y0 edit field. As this system is also starting from rest, the initial time t0 remains 0. Once you have added all the relevant parameters, you will observe that the specify solver option automatically changes to ODE 15S from ODE 45. Now, click on the Solve ODE dropdown and specify the start and end times. We are going to change the end time to 10. I will repeat the changes that we have done in this Solve ODE task. In this stage 2, we are trying to solve the system of equations of differential algebraic equations of the format m dy by dt is equal to f of ty. For that purpose, we have selected the second option in ODE type. After selecting this option, the parameters of the task are updated, and for the ODE function, we will select function handle and write the name of the local function that we had created. In this particular case, we had created the ODEFUN function. For the mass matrix M, click on the drop-down and select mass matrix. We have then added the initial value y0 for this system of equations. The solver automatically got updated to ODE 15S, and then we modified the end time for solving the ODE to 10. Once you have made all these changes, click on the Run button to run the current section and see the plots. All the steps have been posted in the chat for your reference. If you are able to complete this step, please put a thumbs up in the chat window. Thank you for confirming. The actual equations governing the parachute deployment are significantly more complex than the simplified example that we just saw. It's more complex because of the non-linear drag forces, time-dependent parachute dynamics, coupled motion of the skydiver and the parachute, and environmental factors like wind and air density. However, this simplified example serves as a stepping stone, allowing you to expand the model by including various complexities for the development of accurate and reliable simulations of the parachute design. We now move on to the third stage, where we want to model the external environmental effects on the descent. The third stage is divided into two steps. The first, where we will investigate the air resistance variations. During the descent, varying air resistance is a critical factor. These variations directly affect the stability and the rate of descent. So, modeling air resistance provides a way to simulate and understand how the external environmental factors like air density or changing parachute drag impact the descent performance. For this purpose, let us consider a second order differential equation of y double dash is equal to a by b t of y. Now, as we have seen in the stage 1, that we will convert a second order differential equation into a system of first order differential equations. So let's rewrite this second order differential equation as a system of first order equations, and we get two equations, that is y dash of y1 dash is equal to y2 and y2 dash is equal to a by b t of y1. For this, we are now defining the function dy dt, that is the ODE FCN, for the air resistance variation. This particular function has four input variables, t, y, a, and b. These four variables are the parameters for air resistance, the initial conditions, and the time range for simulation. So let's specify these variables one by one. We will specify the values in line number 57. A is equal to 1, and then the mass or the effective area related factor B is equal to 2. The time span or, for simulation that we are considering is T span is equal to 1 to 10, 1 to 5, sorry, 0 to 5. And then the initial conditions Y naught as 0 and 0.01. These values have been added to the chat window for your reference. I will repeat. Currently, we have added four parameters here. The arbitrary scaling factor for drag A, which is equal to 1. Mass or effective area related factor B, which is 2. The time range for simulation, that is T span from 0 to 5. And the initial conditions for position and velocity Y naught as 0 and 0.01. We are going to solve this equation using the ODE 23. So let's write the function for this. Add the particular line of code in line number 63. The code has been added for your reference in the chat. Once you have added this line of code, you can run this particular section to see how the air resistance is modeled. I hope you were able to follow along till this. Please put a thumbs up in the chat section, in the chat window. To run this, thank you for responding. To run this particular section, go back to the live editor tab in the MATLAB toolstrip and then click on Run section. I will repeat. To run this particular section, go to the live editor tab in the MATLAB toolstrip and click on Run section button. This step models the air resistance, which is core external environmental factor during descent. The results inform how the drag-induced changes might affect the skydiver's trajectory and velocity, aiding in optimizing the parachute design or descent safety. Now, let's move to the second part of this stage, where we want to model the parachute oscillations due to the wind forces. During descent, the oscillations caused by the wind forces can destabilize the parachute skydiver system. So, these oscillations need to be analyzed to ensure stability and minimum hazards. For this, the wave equation provides a framework to model these oscillations dynamically. To solve this wave equation, we are going to use the PDE modeler app. So, go to the MATLAB window. I will repeat. We are going to use the PDE modeler app to solve this wave equation. So, go to the MATLAB window and in the MATLAB toolstrip, go to the Apps tab. Go to the Apps tab. In the Apps tab, click on the drop down for Apps and then search for PDE Modeler. I will repeat. To solve the second step of the second step, we are going to use a PDE Modeler app. For that, go to the MATLAB window, navigate to the Apps tab, and then search for the PDE Modeler app. Once you have found this, please click on the PDE Modeler icon. Please give a thumbs up in the chat window if you are able to open the PDE Modeler app. Thank you for responding. Now, to solve the wave equation using the PDE Modeler app, we will first display the grid lines by clicking on the options and then selecting the grid. I repeat, we want to display the grid lines. For that, go to the options menu and then select grid. Once you select grid, you can see the grid lines in the display. Also, we are going to select another option called snap so that whatever new shapes we are using will be aligned to the grid lines. So go to the options and click on snap. To solve this wave equation, we are going to use a square boundary. So let's draw a square. To do this, click on the rectangle button that you can see in the tool strip. You have to click on the rectangle button, the first button on the tool strip. Once you click on that, come to the point -1, -1, come to the point -1, -1, and then click to create a square. You have to click on the rectangle button and then come to -1, -1 point, and then you have to create a square. I will repeat. We are going to use the square boundary to solve the wave equation. So to set up this square boundary, click on the rectangle icon that you can see in the tool step, come to the -1, -1 point, and then drag the mouse after clicking to create a square. Put a thumbs up in the chat if you're able to create the square boundary. I will repeat the instructions to create the square boundary. You have to click and drag at the corner to create a rectangle icon. You have to click it once. After clicking it, come to this point -1, -1. Then left click your mouse, drag it up to 1, -1 point. From here, drag it to 1, 1 point, and then bring it back to -1, 1 point. You'll be able to get a square boundary. You have to drag the mouse once you have left clicked on it. I hope you are able to get the square window. Please put a thumbs up in the chat window. Please drop questions in the chat if you are facing issue to draw a square in the display. Okay, I hope you were able to set the square. We'll move on to the next step. The next step is to specify the boundary conditions. For doing this, let's switch to the boundary mode. Go to the boundary dropdown and select the boundary mode option. I will repeat. Go to the boundary dropdown and select the boundary mode. Now you can see the boundary of the square is defined. We will specify the boundary conditions for each of the boundary. Let's start with the left side. Double click on the left boundary and you will see a boundary condition dialog box open up. I repeat, you have to double click on the left boundary and then a boundary condition dialog box will open up. For the left boundary, we are going with the default Dirichlet boundary. So just click OK. Similarly, for the right boundary, double click on the boundary and you will have a dialog box for boundary conditions. Click OK because for the left and the right boundaries, we are going with Dirichlet boundary condition. Now, double click on the top boundary. Here, we are going to change the boundary condition to Newman. I repeat, select Newman for the top boundary condition, but we leave the values of the coefficients as the default values. Click OK once you have selected Newman as the boundary condition equation. For the bottom boundary also, we are going to use the Newman condition. So select Newman and then click OK. I hope you were able to follow along. Please drop a thumbs up in the chat window if you have completed this step. Next, we will specify the coefficients by selecting the PDE. For this, go to the PDE drop-down and select PDE specifications. I repeat, we want to specify the coefficients for the partial differential equation. So go to the PDE drop-down and select PDE specification. Once you click on it, a dialog box will appear in which you can select various types of PDEs. For this particular case, we are going to use the hyperbolic PDE. Change the coefficient, change the value of the coefficient f from 10 to 0. I repeat, we are going to change, we have selected hyperbolic type of PDE and we have modified the value of the coefficient f to 0. Once you have done these modifications, click on OK. So far, you have selected the boundary, set the boundary conditions, and also specified the type of PDE. Now, let's initialize the mesh by selecting the mesh. For that, select the mesh drop-down, go to the mesh drop-down, and then select the initialize mesh option. I repeat, we want to initialize the mesh. So for that, go to the mesh drop-down and click on initialize mesh. If you want to refine the mesh, you can again go back to the mesh and then click on refine mesh. I repeat, if you want to refine the mesh inside the square boundary, click on refine mesh option in the mesh drop-down. Now let's set the solution times. To do this, click on the solve drop-down and select parameters. Click on the solve drop-down and select parameters. A solve parameter drop dialog box will appear. A solve parameters dialog box will appear in which you can specify the solution time and the initial conditions for the wave equation. In this, we are going to specify the solution time as linspace 0 to 5 till 31. For your reference, we have added this in the chat window. I'll repeat, we are specifying the solving parameters, and for that, we have specified the solution time as linspace 0, 5 till 31. Now let's specify the initial conditions. We have two initial We can set the following initial values to satisfy the boundary conditions. They have been added for your reference in the chat window. Please put a thumbs up in the chat window if you have completed till this step. Once you have added the time and the initial values to satisfy the boundary condition, click on OK. I repeat, if you have added the time and the initial value conditions, click OK. Now we'll select the visualize options. For that, click on the plot dropdown and select the parameters. To visualize the solution as a 3D static or animated plots, select the plot dropdown and then select parameters. You will get a plot selection dialog box. In this dialog box, select color and height 3D plot. Also, in animation, select animation and also select the plot in XY grid. In this plot selection dialog box, I'm repeating, in this plot selection dialog box, you have to select three options. That is colors, height. Colors is already selected. You have to select height, animation, and plot in XY grid. Once you have done, you can click on the plot. I hope you were able to follow along and are able to see the animation. This simulation provides a dynamic representation of how parachute oscillates due to the wind forces over time. By visualizing the wave propagation on oscillatory behavior, this model helps evaluate stability issues and potential vulnerabilities in the descent process. This step directly ties to the external environmental effects, focusing on the wind forces as a destabilizing factor. It emphasizes how oscillations form gusty conditions might impact descent safety and performance, guiding the decisions on material selection and structural design. So, to summarize, in this tutorial, we explored how to use MATLAB to model and solve the different types of differential equation through an example of a skydiver's descent. We started with a simple ODE to demonstrate the free fall under gravity and the effect of air resistance. Next, we introduced a differential algebraic equation system using a mass matrix to simulate a dynamic event such as deployment of a parachute and analyzed its impact on the descent speed. Additionally, we experimented with multiple initial conditions to explore variations in starting heights and velocities. Finally, we demonstrated how to pass extra parameters to the ODE function to study the influence of changing air resistance on the descent. This example gave a simplified illustration of the workflow, but you can use the tool and techniques from this tutorial to create a more accurate model of the skydiver's jump with realistic conditions and forces. Similarly, you can apply these methods to model different types of systems using differential equations. So in this tutorial, we have covered the different ODE solver options available in MATLAB, such as ODE 45 and ODE 23, to solve both uh, first order and second order differential equations. We also solved the differential algebraic equations using MATLAB by incorporating matrices and the algebraic constraints. We also simulated the wave equations and analyzed oscillatory behavior using the PDE modeler app. We have applied MATLAB to model, solve, and visualize solutions for the ODEs, differential algebraic equation, and the partial differential equations. With that, we conclude today's session. We will now share the solution live script with you, which you can use for your further references. In the solution live script, we have added a section, additional resources, which provides link to additional resources, including the MATLAB documentation examples, tutorials, and further reading materials. Thank you for participating in this session. Please post your questions in the chat window if you have any queries. You can all try to download the solution live script and let us know if you are facing any issues with the live script. Okay, thank you all for joining the session. I will now close this session. Thank you.